some of the other properties of ions. We're specifically going to start thinking in terms of conductivity in cells, and to think of these, we're going to have to understand what factors are at play when you consider the speed that an ion travels in solution. So there's some problems in your homework or in your text and the homework I'm going to assign. I don't know if it'll be homework or an exam, but there's some problems that ask you to determine dissociation constants and things like this based on observed conductivities of solutions. And there's a derivation that's done in your text that I kind of want to walk you through real quick. First of all, you stick an ionic solution inside of a container that has two capacitors on it. Your negatively charged capacitor is going to have one potential. Your positively charged capacitor is going to have another potential. And what's going to happen in that solution is that the negative ions are going to start migrating towards the positive capacitor, and the positive ions are going to move to the negative plate of the capacitor. Right? Over here, on the negative side, electrons will get picked up. On the positive side, electrons will get stripped. As that happens, you'll need a current transfer for that system. And so that's what's going on when aqueous systems, or when ionic systems, ionic solutions are conducting electricity, is that electrons are being stripped from the negative ions and being donated to the positive ions. You want to take a look at this and tell yourself what species are going to be formed at those plates of that capacitor as this thing discharges. I'm going to answer the questions, something for you to think about. In general, we have that the voltage of a system is equal to the current times the resistance. And so if you're looking for the current, you need to know what the voltage is and what the resistance of a system is. When I say a system, I need to be kind of careful. What we're talking about is really an object, a piece of material the charge has to flow through. And maybe imagine that this is just a standard resistor. When the charge is inside the material that this resistor is composed of, it's dependent on that material's properties. That material's properties determine how fast it can travel through the material. It turns out that the resistance of a specific piece of material is directly proportional to the length of the material, or the length of the electron's path through the material, I should say. So the further the electron has to travel in the material, the longer that it's subjected to that material's impedance. And so the longer the length of the material, the higher the resistance of that material. With an increased surface area, and right now we're talking about surface area that is perpendicular to the path of the electron's travel. With an increased surface area perpendicular to the path of flow, you have available more paths for electron travel. And so a larger area here is going to effectively generate more paths, therefore there's a lower resistance. So we say that for any material, our resistance is proportional to the length over the area. And when we talk about length, it's length parallel to electron flow, and area is area perpendicular to electron flow. And then rho is just a proportionality constant. And you can imagine that that proportionality constant is going to be a function of the exact properties of that material. So the total resistance is always going to be a function of the shape of the material, the paths available to the electron that travel through it. And then there's just going to be some constant that we can slap on top of that is material based. And that constant is called rho. In your book, they show you that rho gets turned into this thing called kappa. And it's kind of easy to see why defining it as kappa is useful. If we rearrange our expression for V equals IR and turn it into an expression for current, we'd always like to know how much current we can expect to have flow through a material if it's set at a particular voltage. So if we recast this expression in terms of current, we see that the current is proportional to the voltage times 1 over rho. Sorry, I should use K is 1 equal to 1 over rho times that A over L term that we derive from the actual shape of the piece of matter that we're dealing with. And so we're going to define this thing kappa as being 1 over whatever that constant was that was material based. Therefore, rho is dependent on the material, as is kappa, and those are a measurement of the material's ability, its relative ability compared to other systems to conduct charge. For ionic systems, for any system, these things are dependent on the material. Since conductivity, incidentally kappa is called the conductivity. Since conductivity is dependent on ions, and the number of ions, you can imagine that the term kappa is going to depend on the ionic strength of the material. So there's a little bit, this whole ion thing ends up getting a little bit strange, because what you might expect from intuition to have happen inside of an aqueous system of ions and what actually happens are two different things. If you would have asked me before I taught this class, which ionic solution do I expect to conduct better or conduct electricity better, a 1 molar solution or a 10 molar solution, I would have said, well, I expect a 10 molar solution to conduct electricity better because it's got more ions, right? Isn't conductivity a function of the number of ions? But the truth is that's not actually what is observed. What's observed is that ionic solutions conduct electricity best in the limit of infinite dilutions. So an infinitely dilute ionic solution is going to end up conducting electricity better than a concentrated ionic solution. And to understand that, we can go back to this image that we had on our other set of notes. Where we looked at the number of solvating, or the number of ions surrounding an ion of a given charge. In solutions of higher concentration, a negative ion is surrounded by more positive ions on average than it would be in a solution of low concentration. And it turns out that these surrounding ions kind of retard the mobility of the ions in solution. Go back to this other image. If you have a negative ion trying to move towards a positive plate of a capacitor, and a positive ion trying to move towards the negative plate of the capacitor, as these two ions pass each other in their travel, they'll start to feel attractive forces. And those attractive forces will kind of pull in the opposite direction from what the ion is naturally trying to, from the direction the ion is naturally trying to flow. Higher concentration means more surrounding ions, means a smaller R value. If R is the average separation distance between ions, you're trying to calculate the force between them. With a higher concentration, you get a lower R value, therefore the forces that those ions are acting on each other with are larger. And so what's observed is that as you actually increase concentration, those retarding forces end up making the conductivity of the solution lower. And so to express that, we have this equation. We're going to define a molar conductivity. Molar conductivity is the actual conductivity divided by the concentration. So it's kappa divided by concentration. And this value, AM naught, is going to be the value of that conductivity at infinite dilution. So you'll have the largest value of conductivity for an infinitely diluted system, infinitely diluted ionic solution. And then as concentration increases, you're going to have a decline in that activity, or sorry, in that conductivity. And so to describe that, we say that the conductivity at any given concentration is equal to the conductivity at infinite dilution minus this concentration dependent term. And you can imagine as the concentration increases, that the conductivity is decreasing for the reasons that we just discussed. In your book, this constant here is assigned the value of K. I didn't want to put that up right now because we already told you that this conductivity kappa was equal to K. And incidentally, that's even a different, this is actually a different kappa than the kappa used when we looked at the derivation of the Debye-Huckel theory. So there's just way too many K's. But just remember that this kappa here is not the same as that kappa. It's a different K altogether. And that's just to describe this result that conductivity decreases with concentration. So it's difficult to measure the effects on conductivity one ion at a time because the ions will come together. There are methods for doing that. We'll address that in a second. But ultimately, we're going to define these little lambda terms, lambda plus and lambda minus, as the individual conductivities of the negative ions and the positive ions respectively. And so each ion is going to contribute to the conductivity. We saw how in solution the ions are attracted to the different plates of the capacitor and they start migrating. The rate at which they migrate ends up being a function of their specific three-dimensional characteristics and their charge characteristics. And take a look at how quantify that. The way that we quantify that is we say that any moving object that moves through a material is going to have some frictional resistance, and there's frictional forces that are exerted anytime one piece of matter passes another piece of matter, and the magnitude of those frictional forces will end up determining the maximum speed that an ion can travel at in solution. You guys know what terminal velocity is for a falling object falling under the force of gravity? Yeah? What's terminal velocity? You take an object from the top of an airplane and you drop it. Top of an airplane? From an airplane, and you drop it. As that object speeds up, it's going to experience drag as it passes through those atmospheric gases. It's going through millions and millions of collisions with gas molecules as it falls. The faster it falls, the more collisions it has with those gas molecules, and therefore the higher the drag. At some point, if the object is falling fast enough, as its speed increases, the forces of drag increase. If the molecule obtains a speed that's large enough, you'll get to the condition that the gravitational force that is accelerating downward is equal and opposite to the drag force that's acting against the direction of movement. And once those two forces are equal, you get no more acceleration. And so you move at a constant velocity. Your velocity doesn't change. There's an analogous thing going on inside an ionic solution. The force that's causing the ion to be pulled is the force of the charges on that capacitor, right? Those are pulling the ion, the positive charges on the positive plate are pulling the negative ion towards it. And they're acting to accelerate the ion towards itself. Simultaneously, as that ion moves in solution, it's passing all of those other positive charged ions, plus it's passing all of these solvent molecules, all of which exert attractive forces to it. And so its motion is being resisted by the forces from the other objects in solution with it. And the faster it moves, the greater the magnitude of those forces becomes. And so the drift speed of an ion is analogous to that terminal velocity for a falling object in gravity. A force that acts to speed the ion up, or to move the ion towards the capacitor, is proportional to the charge on the ion. So we're going to write the charge, E is the charge on one electron, times the Z, which is the coefficient on the ion, it's the 2 plus ion, 3 plus ion, etc., times the E field. So the magnitude of the force that the capacitor pulls on the ion with is proportional to the field generated by the capacitor, the charge on the ion times the Coulomb charge, or the charge of one electron. The resistive forces on that ion are summed up like this. You've got this N term that is a function of the viscosity of the material through which the ion is traveling. So the larger the magnitude of N, the larger the magnitude of those resistive forces are. A is the radius of the ion. And so, without deriving this, I'll tell you that the reason the radius had to be incorporated is because when you try to factor in, you try to see how great the forces of friction are that are acting on something, you need to know how much surface area is available for those frictional forces to make contact with. And so the larger the A term is, then the larger the surface area is around that ion. And so a larger A value results in larger frictional forces for that ion as it tries to make its way through the solution. So we have this term here that describes the magnitude of the frictional forces. They're multiplied by the speed. So that S is the speed. They're dependent on the radius of the ion, the viscosity of the medium. We set those two expressions equal to each other, and we get this term for the drift speed, which again is analogous to the terminal velocity for a following object. And it goes as the charge on the ion, the magnitude of the field, divided by this term, which quantitates the spherical surface area around the ion and the viscosity of the medium. This term gets turned into a mobility, where we define mobility by saying that the drift speed is equal to the mobility of the ion times the field. And so, based on what we derived up here, mobility is equal to EZ. I should have gotten rid of that E. That doesn't belong there. Mobility should just be E times Z over 6 pi times the viscosity of the media over the radius A. So get rid of that E right there. That doesn't belong in the expression. And then just this expression over here that says that mobility or the individual conductivity of an ion depends on its mobility times its actual charge. And so the take-home message is that an individual ion's conductivity is dependent on the charge of the ion, the viscosity of the medium it's traveling in, and the actual size of the ion. So those mobilities of individual ions can be measured, have been measured, and what I want you to do is I'd like you to go look at, I forget which example it is, the table. There's mobilities given in table 9.1 or 9.1, and example 9.1 shows how ionic mobilities can be used to measure the dissociation constants of weak acids. I'm probably definitely going to include one of those problems in your take-home exams, so do review those. One other thing that I wanted to say about this, your book addresses it, or maybe it's not your book that addresses it, maybe it's a different book that addresses it. It might be your book, you can double check your text to verify. The expression that we derived earlier for the mobility of an ion suggests that mobility will depend on the radius, and that therefore smaller sized ions are going to travel faster than the larger sized ions. If you actually look at the data on the drift speed, the calculated or determined drift speed of these ions, you'll find that the smaller sized ions actually end up traveling at slower rates than the large sized ions. And that's not what we expect. We expect the radius of the ion to be proportional to the, or inversely proportional to the drift speed. And what the explanation for this is that a moving ion carries with it all of its water molecules. it's not just the water molecules that are butted right up next to the ion that get carried with it. There's also, other water molecules that kind of linger. And so you kind of hang on to that area. And it turns out that the smaller ions carry more water molecules with them. And so effectively, they've got that unit has a larger R value and experiences more frictional forces as it tries to travel through solution. And so a larger ion you might expect it to travel more slowly, but because it's only carrying around a very few number of waters with it, it's called a titration shell, it actually has an effective radius that's smaller. So this kind of goes against what we decided about the effective radius when looking at solvation enthalpies or delta G's of solvation. But while the effects are both due to water, the fact is that when these ions are moving, they're carrying all of their solvated waters with them, and the large ions can have fewer solvated waters than a small ion. And so the small ion actually travels at a smaller rate than the large ion. This works out for all of the ions except for H+. H+ travels very, very fast in solution. And that's really not expected because it's the smallest ion, and based on what we just said, for small ions it should have the greatest solvation shells. Well, H+ doesn't travel solvated by water molecules, it travels on water molecules. So H+, that theory of solvation shells doesn't really exist. And they show you a mechanism where the H+ jumps from one H2O to another as it moves across the solution. And so H+ disobeys their conductivity laws for those. Okay, so that was the part that's nice and clean, and now you get the dirty part for the next 15 minutes, and that is because, again, as I was trying to copy notes on the thing, this time they kicked me out of the computer room. They said, computer lab's closing, everybody has to leave, you can come back at 5 o'clock if you need to use the computers. And that doesn't do any good, right? Because at 5 o'clock, the lecture's already done. So now I got to talk this last piece to you. I'm sorry, it's going to be kind of dirty, but I'll put some notes together and try to clean it up for you in the notes. Just listen for now. Just unplug the thing, why is it still running? Okay, so I'm going to make this quick. I'll put together some notes like the last set that you can read and try to explain this stuff a little bit more carefully. But we're to the point where we're going to start talking about electrochemical cells. And for an electrochemical cell, you're going to be given redox half reactions for each of your redox pairs. So for instance, you can look up redox half reaction for the reduction of copper, aqueous, and that's going to be equal to, it's going to look like this, Cu2 plus 2E minus goes to Cu solid, and you're going to get a half cell potential that's equal to E naught of V is equal to 0.153 volts for copper. There's tabulated half cell potentials for all kinds of ions and their oxidized and reduced forms. these are all measured by defining the half cell potential of a hydrogen electrode as being 0. And so we take as a standard the reduction potential of hydrogen, 2H plus 2E minus goes to H2 gas. We assign that a voltage of 0. So with the voltage, with the half cell voltage of hydrogen defined as 0, you can go look at cells composed of hydrogen combined with other positive, with other half cell reactions, and you can tabulate the half cell potentials for all those other reactions by relative to hydrogen by assigning hydrogen a value and not value of 0. With this convention, we're going to end up calculating delta G's for reactions. It turns out that delta G for a cell, when it's done reversibly, the charge is transferred reversibly, is equal to charge transferred times the voltage, and the charge will be the charge on each ion. We'll call that V, is the charge on the ion, and multiply this by Faraday's constant. That gives us the total amount of charge. So the coefficient on the charge for the ion times the Faraday's constant is the total charge. And voltage is E, and we have that delta G is equal to negative VFE for electrons transferred through one of these cells. We know that for spontaneity, delta G has to be negative. Therefore, the E of that cell has to be positive. The E of the cell is the combinations of the E of the two half cells. And so when you're running these reactions, you've got to ask yourself, first of all, no two half cells that are combined together are both going to be written as the reduction, right? One will be oxidized, one will be reduced. And so you'll have to flip one